Hi, my name is Peter Felfer, and today I'm showing you how to do clustering analysis using the voronoi clustering. It's part of my OpenVA software packages that I'm starting to distribute now. And what it actually is a cluster analysis based on concentration fields. And the way that a concentration field is defined in this case is by the volume that each atom that we're testing the clusters for is uniquely occupying in space, which is its Voronoi cell. This distribution is, of course, much more useful than, or has a lot more uses than just cluster analysis. But cluster analysis is one of the most straightforward ones. You can also use it to, for example, separate grain interiors from grain boundaries, which is another thing that I'm working on for nanocrystalline alloys. But today I'm showing you how to do the cluster analysis. The program's actually written in MATLAB, and you should have the code distributed in an email earlier. And what you need to do is you open MATLAB, and the first thing you do is you type in the command MATLAB pool open. And what that does is actually starts MATLAB instances on the different cores of your computer, so you can actually make use of multi-coring. And in the end, you should see a symbol like this one here, like this 4-core symbol. In this case, it's a quad-core Xeon processor. And it's very important because it means that the analysis is going to be 4 times as fast, and it makes a huge difference, of course. If you've got an 8-core machine, you're luckier, you can run it on 8 cores. Anyway, next thing is you'll start the clustering program itself. If you're in the right folder, of course, and you just type in Voronoi clustering, it's a graphical user interface, and it's very easy to use. And you actually work your way from the top to the bottom. So we're starting by loading in the files, and I'm using one that I've a POS file, atom probe data that I've acquired together with a colleague from UC Santa Barbara, Betsy Clark. And you can see here that's already something where I've chopped up the data set using the other programs, and now we just have the bulk part of the data set, and that's what we're analyzing. The next thing you need is an Xrange file, which is the windowing file type that I'm using. Is something that I've developed myself. It's XML based, so if you program yourself, you might appreciate that because any programming language that you work with will have an XML parser, and you can just simply load it in and you will be straight away able to use it. If you need to create, you probably need to create Xrange files for your dataset. You just go onto my webpage and download the Xrange editor, and it can deal with .pos and .epos. I haven't implemented .ato, but .pos and .epos are fine. You can load it in. You can create an Xrange file, and then you can use it for the analysis here. Just click open. And then the next thing you will see is you'll have the different elements that are in your data set. You'll have appearing here in the list box to choose from, so that you can choose which elements you want to perform the cluster tests for. In some cases, you might actually want to perform different cluster tests for different atoms because they're not co-clustering. In this case, we only have one type of clusters, which are mainly aluminium and nickel. So we'll test for aluminium and nickel clustering. And the only thing we need to do for that is choose aluminium nickel, obviously, and press perform analysis. Then it will kick off and do the spatial tessellation, the Voronoi tessellation of the dataset, and calculate the Voronoi volume of each of the atoms. And we'll come up with a calculation at which threshold we have to consider an atom to be more likely clustered than unclustered, and we'll come up with an n-min that I will explain a little bit later what it actually means, because it's not a really firm value. There's 2 types of n-min values that make sense, and actually theoretically more than just 2 types. You will see here you've got the weight bar that tells you how far into the calculation we are. And this weight bar will actually appear twice because we calculate the Voronoi volumes of our experimental distribution of the atoms, and we compare it to a randomized distribution. Randomized because the atom probe dataset might have or most likely has density fluctuations due to a variety of effects that can happen, and so we're randomizing the data set rather than using a spatial random data set to compare it to. And you can see here, because we're running it on multi-core, we're maxing out all 4 cores in our system, and that's actually good. That's what we want. And now I'm going to pause the recording, and I'm going to wait until the calculation is over. You can see it takes about a minute and a half for the experimental distribution, another minute and a half for the random distribution. So plus a little bit of other overhead, maybe 3.5 minutes or so for the entire analysis. This is a data set of about 10 million atoms, and it contains a couple of 100,000 atoms that we're testing the clustering for, so pretty typical size. And it scales pretty linearly with the size of your data set. But yeah, no, I'll pause the recording and I'll wait until it's finished. Alright, after a couple of visitors to my office, I'm finally able to resume. The analysis itself took about, I don't know, 4 minutes or something, even though now it's a little bit later, if you follow the clock down here, because a couple of people asked me things about this analysis as well. For example, what you can export it to, and I'm going to show you what you can export it to in a little while. So you get these two windows, and the first one is the actual voronoi volume analysis, and the other one is the cluster size distribution. So as you can see here, you've got the voronoi threshold filled in for you, and nmin as well. And what the voronoi threshold is, first of you have the voronoi volume distribution that experimentally measured for the aluminium and the nickel in this case, and we compare it to a randomized distribution, which is the green one. I will actually change that to say randomized rather than random, I think. And then you experimental versus random, and this area here, until it goes to 0, is where the atom with a certain voronoi volume is more likely to be clustered, so more likely to not belong to a random distribution than it is to belong to the random distribution. And as long as this is the case, we assume that it is clustered. So this is our cluster cutoff. It's about 0.116, so it would be around about here, and that is because there's histogram binning. And you can go and check whether that's actually precise. So you can see here that's the volume you got, but because the histogram bin ends here, it is probably better to take. But you can see it's crossed it here. It's closer to 0.19, so we can actually change that to 0.19. But usually, if you've got a larger data set with better statistics, that's usually pretty spot on. Anyway, in this case, I'll just change it just to show you where the value comes from. And then you've got the min value, and but the other thing to mention is that the integral of this is the percentage of atoms that is clustered. So you get a cluster percentage in this case of about 6%. And the other thing is the cluster size distribution, and what that is a histogram of the cluster sizes. And the way the histogram is calculated is actually it's dynamically binned, which means that a bin is created wherever there are. Sorry, it was a bad zoom. Set to original view and horizontal zoom only. So for every cluster there's a bin created, and if there's multiple clusters with the same amount, then the frequency is this amount. And if there's only one cluster with a certain size, then we measure how close in size there are clusters and divide it by that amount, so that you can get dynamic binning very easily this way. And you can see we can get the curve even if the statistics are not that great. And the one thing you can see here is that the random curve, the random clusters above 10 or 15 are very unlikely. And here we also found one with 80, but there's the really important, the really significant clustering sets in at about 15 here. So you can see here that there's a certain amount, there's a certain level of confidence in what is a random cluster and what is a significant cluster. And the largest cluster that we found a random distribution is at 78, but that's really more of an if I have a cluster with 78, it's very likely to be non-random. Whereas here, these two curves, if you go to a small cluster size, you can see here, it's more likely that the cluster is actually random than non-random, and once you go beyond about 10, it's very unlikely that the cluster is non-random. As a good cluster cutoff here, I would say that up to here, depending on what you're after, it would be really around about 20 uh, as the cluster cutoff. But this is really a matter of what your clustering level would be. If you're after smaller clusters, of course, you can go here as well. The next step is then to export our filtered data, and to do that, you just click on the button, and you get the options of what you can export. You can export the cluster test report. You will, of course, usually do that just to remember which datasets you've used and what the values were that you got out of your analysis. Then the test atoms. And this is the first thing I'm going to export. So we're just going to export the aluminium and the nickel atoms that are classified as clustered. And I'll just put it into the folder that I've created for the analysis, which is here. And that is clusters aluminium, nickel. And you can save it either as a POS file, or as an OBJ file, and you can use the OBJ file for display in Blender and other computer graphics programs. I'll just go and save that. And if I go and open it in 3Depict, so just go Control Open and desktop, and where is it? Where's it gone? There we go. Alright, there seems to be something wrong. I'll just pause the recording and start 3Depict. Okay, must have been a bug in 3Depict. I had to start it up again. So I'll just give it an orthogonal perspective. And there we've got our filtered clusters. But 3Depict actually has a very handy option, which is the monitor file option. So whenever we change a file, it will update the POS file. And my program knows that as well. So if you change nmin, it will actually redo the nmin cluster definition and overwrite the file. So if I would type in 50, it updates that. 20 is what we had originally, and that's our cluster nmin that we're using in this case, because that was where the sort of the linear tail of the distribution was. So if you look here, that's really where it ends. So maybe 25. Okay, we should probably do it correctly. So it bottoms out here. So we should take this value as the min value, and it would be 23. So we'll go with 23, and there we go. These are our clusters. And the next thing we're going to export is the cluster locations, which is the center of mass of each cluster. And the reason why that is important is because you can use it to calculate the point axis, the feature axis of each of the clusters, which is a very good metric for the composition of the clusters if you have got small clusters. that have larger trajectory aberrations on them, which means you're determining only how the concentration changes at the cluster, and this is independent of all the aberrations that you find in atom probes. So it gives you a pretty good measure of the cluster chemistry. And you can also use it for, my colleague Vic, for example, wants to use it to map to get cluster proxygrams and things like that. Anyway, just choose cluster locations. You can, by the way, export more than one at a time. So it's cluster locations dot pos. Save that, and you can open that in 3D Pict again. Cluster locations, open. Of course, you can't see very much yet. So first of all, we're gonna give them a different color, make them green, and probably a little bit larger. And there you go, the cluster locations. And the actual fourth value of the cluster location is the amount of atoms that are in the cluster. So if you go, and we'll just remove the ion sampler, if you go and put on an ion color on there, you can see from the color how large it is. I think the largest one is probably larger than 100, maybe let's type in 300. You can look up how large the largest one is. Maybe not. How large is the largest one? The largest one is actually larger than that, but there's not that many of them, so probably if you want to look at the finer one, the cutoff at about 200 would be appropriate. You can see the size of the larger of the many smaller ones, and then you see larger ones. I'll just switch that one off so you can see that the larger ones are sitting towards this direction here. So this is also a very very helpful analysis. And I think 3D Pict is gone again, but that's what I wanted to show you in 3D Pict anyway. The next export is clusters, the convex hulls, which are really the envelopes of the clusters. So just select that, and we'll go to precipitates again and call that cluster hulls. Nickel aluminium, save, and we'll open that in Blender, which is my favorite 3D program, and delete the default cube, and go file import wavefront obj, and it is somewhere on the desktop, wherever there we go. And there we go. So you can see these are the hulls of our clusters. That's also the reason why you can export the atomic positions as .objs, so you can actually have the cluster hulls and the atomic positions as both OBJs here. You can use that program for all sorts of things in Atom Probe together with my programs. One of those things is, for example, clipping out volumes. So if you just want to analyze certain parts of your Atom Probe dataset, you can create a volume in Blender and use that to clip your Atom Probe data. It will distribute these programs as well. Yeah, and this is pretty much it. What have I not covered here? Clusters all atoms just means you export all atoms that are within the convex hulls that I've shown you before. That's the difference. I don't think that's pretty self-explanatory if you want to do some sort of analysis in an external program. Alright, and the last thing you can do is compositional analysis. And I'll just show you for the contained atoms what that does. You just click contained atoms and OK. And what it does is it calculates for each cluster which atoms are inside that cluster, and then it calculates the chemical composition of each cluster, and you get that back as a .csv file, which is really great for analysis, for example, in Excel. This will take a minute or two, and I'll pause the recording again at this point. Alright, that's finished, so we can save that analysis as well together with the others. And yep. cluster concentrations.csv, and we'll save that. And just to save some time, I'll pause the recording again and open it in Excel. Alright, there we are in Excel. And in order to import the data, all I need to do is go into Data. From Text, you'll go wherever it's saved. Cluster concentrations, import, delimit it, and delimit it by space. And there we go. And that's all we need. And we'll put it in here. And you've got your different concentration and the size of your cluster right here. So if you want to, usually you probably want to sort it by the size. So just go and mark all of this and sort by number of atoms, largest to smallest based on values, and there we go. You'll get your, for example, what can we get? Nickel versus cluster size, and you can have that as a scatter plot. So you can see the cluster size here, the nickel content here. So you can see there's a lot of spread in terms of nickel content for the small clusters, but the larger the clusters get, the more they're moving really towards a certain amount of nickel in them. Alright, that's it. Give it a try. Tell me what you think of it. Was it useful for you? And is there anything else that you want to have implemented in the voronoi clustering?